In the last lecture, we have seen how to obtain the parameters of the approximate equivalent circuit of a single phase transformer. The approximate equivalent circuit looks like this. This is the supply voltage V1, magnetizing current I0, supply current I1, Req, J Xeq is the referred load current I2 dash, and this is the referred load voltage V2 dash. While this equivalent circuit is important for finding out different performance parameters, from a user point of view, certain performance parameters are very important. For example, one of the most important performance parameter is the efficiency of a transformer. Now, efficiency, as in the case of any other power processing equipment, for a transformer the efficiency is defined as, the symbol is nu, is defined as output power divided by the input power. Now, what is the difference between output power and input power? It is the losses. So, this can also be written as output power divided by output power plus losses. Now, what are the different losses that can occur in a single phase transformer? We have seen the first element is the core loss resistance. This is the loss due to hysteresis and eddy current, and in the equivalent circuit we represent it by a resistance. And the second major loss that can occur is in the winding resistances Req. Therefore, the losses can be broken down into two parts. Plus core losses plus losses in the winding resistance. This is called the copper loss. Now, even from the equivalent circuit, also from the physical principle due to which this losses takes place, we can argue that this core loss depend on the applied voltage and frequency. But single phase transformers are normally connected to voltage sources of constant magnitude and frequency. Therefore, the core loss occurring in a single phase transformer is more or less constant, it does not depend on the load. However, the losses occurring in the winding resistance, they do depend on the load current magnitude and is given by I square Req. Therefore, in terms of equations we can write output power is equal to V2 dash I2 dash cos phi, where phi is the load power factor angle. This is same as V2 I2 cos phi. Core loss is given by V1 square by R0. We indicate it as P core or P iron, and this is usually constant. Copper loss denoted as PCU equal to I2 dash square Req, or it is I2 square Req dash, same thing, I2 square Req dash. Therefore, efficiency nu can be written as which again can be written as in a general transformer, the variation of V2 dash with I2 dash is usually very small. So, for all practical purpose, V2 dash can be assumed to remain constant at its rated value. Furthermore, if we assume that the load power factor also is constant, then we can say that the efficiency depends only on the magnitude of the current I2 dash, and it will be interesting to find out at what value of I2 dash this efficiency becomes maximum. Now, if we look at the expression of the efficiency, we see that it is V2 dash cos phi divided by V2 dash cos phi plus Pi by I2 dash plus I2 dash Req, of which the numerator is constant, the first term of the denominator is constant, only these two terms are functions of I2 dash. For nu to be maximum, the denominator should be minimum. Now, of the denominator the first term is constant, so the sum of the second and third term should be minimum. So, differentiating this quantity with respect to I2 dash, we get the condition for maximum nu max is Pi equal to I2 dash square Req, that is Pi equal to PCU. The load current at which the fixed iron loss becomes equal to the core loss is the load current at which the efficiency is of a single phase transformer is maximum. Now, while it is possible to, if the load parameters are given, it is possible to find out I2 dash and the efficiency under any given load condition, it is usually the practice usually is to find out these values from the test data. The other day we have seen how to find these loss components. We have seen that in the open circuit test, we connect a wattmeter, the wattmeter reading is equal to the core loss, because there is no current, almost no current flowing in the transformer, the no load current is very small. Similarly, from the short circuit test data, we argued that the magnetizing current is very small, therefore, the core loss is very small. So, the wattmeter reading actually represented the copper loss. Now, short circuit test is usually done at the rated current, therefore, the value we get is the full load copper loss from short circuit test. Similarly, from the open circuit test, we get the iron loss, which is independent of the load current and constant. So, let us say from the no load test data, we get the wattmeter reading to be Pi. Short circuit test data, we get the reading to be PCU. Then from these data we can find out the load at which the transformer efficiency will be maximum. The load, the kVA load on a transformer is equal to V2 I2 at any load current I2. The corresponding copper loss equal to I2 square Req dash. The full load copper loss as obtained from the short circuit test, PCU, let us say this is at x fraction of load, PCU at full load is equal to I2 full load square Req dash. So, PCU x by PCU equal to I2 divided by I2 full load square. This is same as V2 I2 divided by V2 I2 full load square, which is same as the fractional load x square. Therefore, the efficiency at any fractional load x can be written as efficiency at a fractional load x equal to x times the kVA rating of the transformer into cos phi divided by x times rated kVA into cos phi plus Pi plus x square PCU, where PCU is the full load copper loss of the transformer. And we have seen that the efficiency, the fractional load at which the efficiency of will be maximum, then Pi is equal to x square PCU, or x equal to square root Pi by Pcu. So, this is the fractional load at which the transformer efficiency will be maximum. Now, this realization has something to do with the design of a transformer. It is natural that we would like the transformer to be as efficient as possible, because that will reduce the energy loss, which means that the transformer should ideally be always operating at the load at which its efficiency is maximum. However, it is not possible to guarantee that for all types of transformer. For example, the transformer that are used in transmission are almost always loaded up to their full capacity. Therefore, while designing a transmission transformer, we would like to make sure that its maximum efficiency occurs near the rated load. However, the situation is very different for a distribution transformer. A distribution transformer for a large part of the day remains lightly loaded or even remains on no load. Therefore, for a distribution transformer, it is important to design the transformer such that the maximum efficiency does not occur at full load, but at a reduced load. Usually for a distribution transformer, it is not unusual to have the loading corresponding to the maximum efficiency at around 60 to 65%. From this discussion, we also can conclude one more thing, that getting the transformer efficiency at a particular load does not give the full picture, because the loading of a transformer can vary over a day. Normally, it is expected that the loading pattern of a transformer will repeat over every day in a season at least. Therefore, a more useful parameter in order to find out the performance of a transformer is called the all-day efficiency. How do I define all-day efficiency? This is defined as energy output of the transformer over a day divided by energy input to the transformer over the day. Now, had the transformer been uniformly loaded over the day, then this all-day efficiency would have been same as the efficiency of the transformer at a given load. However, it is not so. Let us say a transformer is loaded say 25% of the time at, let us say, 50% of the load, time, load, that is x, then 50% of the time, let us say loaded at 80% and let us say 10% of the time it is loaded at 100%. And for the rest of the 15% of the time it remains at no load. Now, if this transformer has a copper loss of PCU at full load and Pi is the core loss, then the losses will be copper losses particularly will be 0.5 square PCU, here it will be 0.8 square PCU and here it will be PCU and here it will be 0. The core losses however will always be Pi, 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 here also Pi. Let us further assume that these loads have power factor, let us say at 50%, let us say this power factor is 0.8 lagging, this power factor is 0.9 lagging, this power factor is 0.95 lagging, and here since there is no load current we do not mention the load power factor. So, let us calculate what will be the all day efficiency. The energy output over a day, if let us say the transformer kVA rating is kVA rated, then the energy output over a day is equal to 50% 0.5 into 25% of a day, that is 6 hours, 1/4 is 6 hours, it remains loaded at 50%. So, 0.5 into kVA rated into power factor is 0.8 into 6 hours, so many kilowatt hour at 25% of the loading plus 85% of the loading into kVA rated into power factor is 0.9 into 12 hours plus 100% of the loading, that is 1 or kVA rated into 0.95 is the power factor into 10% of the time, that is 2.4 hours plus 0% loading, that is no output for another 3.6 hours. So, this is the total energy output of the transformer. What is the total energy input? E in is equal to E out plus E loss. How do I calculate the losses? Losses we can find, since we know that the core loss remains constant at any loading and the copper loss is given by these values. So, total energy loss is equal to E loss equal to 24 hours into P I plus 6 hours at 50% of the load. So, 0.25 into PCU into 6 hours plus 50% of the time at 80% of the load. So, 0.64 into PCU into 12 hours plus rate full load for 10% of the time, that is PCU into 2.4 hours. So, this is the total energy loss. So, new all day equal to E out divided by E out plus E loss. This is how one should calculate the all day efficiency of a single phase transformer, and that the only data we need to calculate this all day efficiency are the copper loss at full load, which can be obtained from short circuit test data, and the core loss, which can be obtained from open circuit test data, and of course, the loading pattern of the transformer. If these data are given, then the all day efficiency of a transformer can be found. Now, one of the effect of these losses is to generate heat and increase the temperature of the transformer. We have found out how from open circuit and short circuit test we can find out the core loss and the copper loss of a transformer. However, during open circuit test there is no load current flowing. So, the transformer is subjected to only core loss. Similarly, during short circuit test the core loss is negligible, the transformer is subjected to only copper loss. So, in none of these tests this transformer usually sees both the loss occurring simultaneously. Therefore, it is not possible to find out experimentally the temperature rise that will occur in a transformer when it is actually used. However, this test is very important from a user point of view, because during use the transformer will be supplying load, hence it will be subjected to core loss and copper loss simultaneously, and as a result the final steady state temperature rise will be determined by the total loss. Now, it is possible to find out the temperature rise of a single phase transformer by test, but not from no load test or a short circuit test. The test by which we can find out the temperature rise of a single phase transformer is called the back to back test or Sumpner's test. As we will see shortly, this test cannot be performed with a single transformer. We will need at least two transformers, and these two transformers should preferably be identical, at least their voltages should be very close or identical. The way it is done is the two identical transformers are taken, their primaries are connected in parallel. And it is supplied from a rated voltage source. Of course, some meters are to be connected, means you have to connect a ammeter, you will have to also connect a wattmeter. The secondaries of the transformers are connected in series with this polarity. Here again another ammeter is connected, another wattmeter is connected, and these secondaries are supplied from a variable voltage source. So, how do you subject the transformers to simultaneous core loss and copper loss? It is like this. Let us assume that, let us apply superposition theorem. Let us assume one source at a time. So, we replace this by a short circuit. Since these two transformers are identical, the voltage generated across their secondary winding will be same, provided since they are supplied from the same source. Therefore, there will be no circulating current flowing in the secondaries, because the induced voltage in one will oppose the other. The current drawn by these transformers will be only the no load current of these two transformers. Similarly, if we short the source V1 and consider the contribution of the source V2, we see that the current flowing in the secondary windings will see two shorted primary coupled to them. Therefore, the current flowing through the transformer can be controlled by controlling these voltages to be the rated current of these two transformers, and the power drawn will be the copper loss of the two transformers. Therefore, when source V1 is present, V2 is shorted, the power drawn is simply the core loss of the two transformers. Now, when V1 is shorted and V2 is applied, then the power drawn is the copper loss of the two transformers. When both are applied, let us say if current is circulated, I2 current circulates this way. Therefore, the reflection current here it will be I2 dash flowing in this direction, and similarly I2 dash flowing in this direction. However, if these two transformers are identical, then this I2 dash current will circulate only in the transformer primary winding. The current drawn from the source will still be 2 I0. Therefore, during this test, the total power drawn from the two sources V1 and V2 will be the sum of the core loss and the copper loss, and since the transformers will be subjected simultaneously to core loss and copper loss, their temperature rise will be same as that when they will be in actual use. So, in this case we see that we can simulate actual loading of the transformers without drawing the required power from the source. That is why it is called a back to back test, and this is a general principle. In many electrical machines we will see such equivalent circuits for back to back tests, because it is important for any electrical equipment to be tested at its rated capacity. However, it is also inconvenient, particularly if the equipment is of large rating, to actually load the equipment and test it. Therefore, for almost all electrical machines, some form of back to back test becomes important, and this is the way the back to back test is performed on a single phase transformer. We will end this lecture by looking at a exercise of how to find out the equivalent circuit parameters of a single phase transformer from test data and how to find the efficiency. Let us say we have a 200 volts by 400 volt transformer. Single phase transformer. The kVA rating is 4 kVA. Let us say the no load test data of this transformer is, the voltage rating is, no load test is of course done on the LV side. The test data is, voltage reading is 200 volt, since rated voltage is to be applied. The current drawn is 0.7 ampere and the wattmeter reading is 35 watts. The short circuit test data this is done on the HV side. The applied voltage is 30 volts, the circulating current is 10 ampere and the wattmeter reading is 90 watts. How do I find out the equivalent circuit parameters of this transformer? Then at no load, the equivalent circuit of the approximate equivalent circuit of the transformer looks like this. This voltage applied is 200 volt. This is JXM, this is R0, this is the no load current I0, this is the magnetization current IM and this is the core loss current IC. The phasor relationship is so if this is the applied voltage VLV, then IM will lag VLV by 90 degree and IC will be in phase with VM. Therefore, the total no load current I0 will be at a power factor angle phi 0 with respect to the applied voltage. Now, from the no load test data, this voltage is given to be 200 volt. and the no load current I0 equal to 0.7 amperes. Therefore, the no load power factor cos phi 0 equal to the VLV I0 W0 divided by VLV 0, this is equal to 35 divided by 200 into 0.7, let us say 0.25. But what is IM? IM equal to VLV by XM, but this is also equal to I0 sin phi 0, and IC equal to VLV by R0 equal to I0 cos phi 0. From the given data, therefore, XM equal to VLV divided by I0 sin phi 0, this comes as 295.08 ohm, and R0 equal to VLV by I0 cos phi 0, this comes to 1.143 kilo ohm. It should be remembered that both these values are referred to LV side, since that is where the test was performed. As we have seen that there are some advantages in expressing them in per unit. For that, we will have to find out what is Z base on the LV side. So, Z base equal to VLV rated square divided by rated kVA of the transformer hence R0 PU equal to R0 into rated kVA of the transformer divided by LV rated voltage square. This comes to 114.3. Similarly, by the same formula, XM PU equal to XM into kVA base rated kVA divided by this comes to 29.508. So, we have seen how to find out the shunt parameter branches of the equivalent circuit and express them in per unit. Let us now shift our attention to the series parameters. In the short circuit test, we can neglect the shunt branch. So, the equivalent circuit is somewhat like this. The applied voltage is VSC, the current is ISC, this resistance is Req, this is JXeq. Hence, ZSC, that is mod ZSC, equal to VSC by ISC. From the given data, this is 30 volts by 10 amperes equal to 3 ohm. Therefore, ZSC equal to square root Req square plus Xeq square equal to 3 ohm. Similarly, the power PSC, short circuit power, equal to ISC square Req. This is given to be 90 watts. ISC equal to 10 ampere. Hence, Req equal to 0.9 ohm. Xeq then will be ZSC square minus Req square. This comes to 2.862 ohm. Now, both the values of Req and Xeq are found referred to the HV side, since short circuit test is done on the HV side. Again, this can also be converted to per unit. So, Req per unit will be equal to Req into rated kVA of the transformer divided by now HV side rated voltage square. This comes to 0.0225 and Xeq per unit will be equal to Xeq into kVA rated divided by VHV square rated. This will give you 0.0716. Therefore, the complete equivalent circuit in per unit of this transformer will be this is XM PU, this is R0 PU, this is Req PU, this is JXeq PU. Here you will get V2 in per unit, here you will get I2 in per unit, here you will get I1 in per unit, this is I0 in per unit. So, this is the how you get the equivalent circuit parameters of a single phase transformer from short circuit and open circuit test data. Now, if I want to find out for the same transformer what will be the efficiency, let us say at 50% of the load. First, let us find out what will be the efficiency at 100% of the load. At 100% of the transformer, kVA rating is 4 kVA. So, at 100% of the load, and let us say at 0.8 power factor, the output power is 4 into 10 to the power 3 watts into power factor is 0.8 divided by the output power is 4 into 10 to the power 3 into 0.8 plus the copper loss, the core loss is 35 watts plus 100% that is at full load, the copper loss is 90 watts. So, at full load the efficiency is 3200 divided by 3200 plus 125, 32 divided by 33.25. This will be the full load efficiency, new full load. If I reduce it to half load, then new half load will be, at half load the power output will be 0.5 and at the same power factor 4 into 10 to the power 3 into 0.8 divided by 0.5 into 4 into 10 to the power 3 into 0.8 plus 35 plus 0.5 square into 90. This will be the efficiency at half load. It will be interesting to find out at what load the efficiency of the transformer will be maximum. Let that load be x, then we know from the condition of maximum efficiency at the loading at which efficiency is maximum, there P I equal to x square P C U, where x is the fractional load. From the short circuit test data, P C U at full load equal to 90 watts and P I equal to 35 watts. So, at what load the efficiency will be maximum? The maximum efficiency will occur at x equal to P I by P C U square root, this is equal to 35 by 90 square root. So, at this load the efficiency will be maximum. It is to be noted that although the actual value of this efficiency is dependent on the power factor, the load at which efficiency or the maximum efficiency occurs is independent of the power factor. So, the plot of efficiency versus percentage load will look somewhat like this. At 0 it is 0, but at different power factor the efficiency curves will peak at the same point. So, these are for decreasing cos phi.